Hey, this is Dr. B, and it's time for week 5 of Chemistry 1100C, and here is the plan for the week. By the end of this week, you're going to learn a bunch of, shall we say, final topics. They vary from everything, including stoichiometry, solubility, energy, acids and bases, as well as oxidation states, and also some stoichiometry as well. So it's quite a bit of material and it's summarized here. Here's the required things that you're supposed to understand that have no point value. And as usual on the next slide, I'll show you the ones that are emphasized. And then here's the activities that have some real point value. I recommend you do all of them. In terms of getting your full 184 points, I would recommend that you make sure you get a full score for the 3 labs that are involved. That's a large chunk of the assignment. Do your best on the quiz, recognizing that it's pretty hard, and also recognizing that we'll be emphasizing the specific types of questions on the quiz in this review. Make sure you get the classroom credit. I'll include the passphrase towards the end of this discussion. Get everything done on time and you should be in good shape. As usual, I do recommend that you pace yourself because it's a recommended 24 hours of work for this week. So take the first couple of days to work on the assignments here. Start the labs, of which there are 3 by midweek. Get that module assignment done. That's this here that is worth 54 points. Get that done and do try to get a high score on that. You should be able to check your work and make sure everything looks reasonable. Then take the quiz towards the end of the week. If you do all that, you'll have nothing to do on the final day. Okay, that's the material we need to know, so let's find out what's emphasized. Here's all the topics that are included in this unit. And should we know them? Yeah, I think we should know all of them. One of them, gram to mole conversions, we learned last week. But are they emphasized on the assignment and are they emphasized on the quiz? The answer this week is that, well, pretty much most of them are. There's about 4 or 5 topics here which we are only going to discuss briefly, either because they're not emphasized or because we did them last week. So let's take a look at these units in order, beginning with limiting reactants. Limiting reactants is what happens out in the world when you randomly mix things but not in the correct stoichiometric proportions. For example, when you click right there on a Bic lighter, you're going to mix some of that butane that's in there with some of the oxygen in the air. But let's imagine that we don't have the right amounts. Let's imagine that you've got 100 grams of butane and 100 grams of oxygen. That's not the exact amounts you need. Let's find out how many grams of carbon dioxide. I'll show you the normal and the fast method. The normal method is to see how far each reactant will take you. Once you run out of that reactant, you're gone. Having said that, the one that produces the lower amount of carbon dioxide will be your answer because at that point you've run out of the reactant. So let's take 100 grams of butane, see how many grams of carbon dioxide it will make. Recognize that's a gram to gram 3-step conversion, so we can set it up like that. Write down what you're given, draw your 3 lines. I'd also recommend you write equals blank grams of CO2 to point out that's where we're going, not to H2O, but to CO2. Well, we have more than a mole because 58 grams of butane is a mole. 12 for each carbon, 1 for each hydrogen. But every mole of butane does not a mole of carbon dioxide make. 2 makes 8, so we're going to write exactly as it looks. 2 makes 8. Notice that a mole of butane is divided by itself, so it cancels. This is going through mole land here, is what some people say. And then we need to go to grams. So always write what you see on the top left, write the same units on the bottom left, and recognize that a mole of carbon dioxide has a mass of 44 grams. Everything cancels diagonally, there, there, and there, leaving us with the desired units, grams of carbon dioxide. In this case, we have enough to make 303 grams of carbon dioxide. Well, at what point do we run out of oxygen? Do the same thing. Set it up nicely. It's 100 grams of oxygen. And this time it's only 32 grams of oxygen as a mole, so we have more than 3 moles of oxygen. However, Every 13 moles of oxygen only makes 8 moles of carbon dioxide. Rather than increasing fourfold, it's not even a 1-to-1 ratio. I think this will be our limiting reactant. Also, a mole at CO2, yes, we're going to CO2, has a mass of 44 grams. So we will run out of oxygen in this system after making 85 grams of CO2. Circle it, that's your answer. Now, there is a faster way to do it, and I'll mention it briefly. I don't know if you want to try it or not. But just do molar amounts and see what you have less of. This literally says that let's see, how should I do this? I'm going to say every 116 grams, that's 58 times 2, requires 8 times 44. Every 116 grams of this requires, God, like 350 grams of that. That's for every gram of that requires more than a gram of that. So 100 would require well over 100, probably more than 300, showing you we don't have enough oxygen. That's called finding the limiting reactant by inspection. 116 grams of butane requires, it should be, yeah, 13 times 32 grams of oxygen. There it is, 13 times 32. I might have been doing the CO2. It requires the oxygen. 2 of these requires 13 of those, which is still over 350 grams. So oxygen is the limiting reactant, so there you go. Yeah, I made an error there. I talked about CO2. I should have been talking about oxygen, but we're going to keep rolling. That's how you do limiting reactant problems. Based on that, you can come up with theoretical and actual yields for reactions. So that's the maximum amount of product. It's the gold standard. It's the perfect score on a test. The actual yield is oftentimes much less, but can be more, for example, if your product is wet. So that's 100. That's usually less. So here's a formula, but I don't think you need it. Like if I said you got a 76 out of 84 on a test, you'd know that your grade was probably B plus, A minus, maybe A minus. And that's what you'd be doing. You'd be taking the actual amount, 76, divided by the perfect score, 84, turn it into a percent, and bada bing. So just think of the percent yield as like your score on a test. And let's try that. The theoretical yield of carbon dioxide for the combustion of 50 grams of butane with excess oxygen. That means it's not a limiting reactant problem. We've got plenty of oxygen. They're telling you the limiting reactant is butane. Is how many grams? You got 25 grams. Let's find out the yield. Okay, what do we start with? We should start with our 50 grams of butane and see how much CO2 it can make. Draw your 3 lines. Also add your equals blank grams of CO2. Same thing as before. 58 grams is a mole, but every 2 moles of butane makes 8 moles of carbon dioxide. Notice how we're canceling diagonally. And every mole of carbon dioxide is 44 grams. We have enough butane, in theory, to make 151.5 grams of carbon dioxide, so that's our theoretical yield. But we only got 25. Now take 25 and divide it by that 155, 1.5. And if you got your score on a test, well, you'd be pretty bummed, right? And that's how it's like a visceral thing. Most students get it. You only got a 16.5% yield. This is theoretical and actual yield. Different topic. Let's switch over to energy and water. We're going to ask ourselves, if you take a chunk of ice, 18 grams, that might be a decent sized cube of ice, and we heat it up all the way to 110 degrees Celsius, meaning from cold ice to hot steam. How much energy does that take? Well, it's certainly going to take a fair amount of energy, right? Imagine putting a chunk of ice on a hot plate and waiting till it's all steam. If you think about it, there's 5 steps involved. First, it has to go from that ice which is cold to the ice which is at 0 degrees. It has to get up to its melting point. Not all ice is at 0 degrees. Ice at the North Pole might be minus 70 degrees Celsius, right? Some crazy number. And then once it's at its melting point, well, it's going to melt. No temperature change, just the phase change. Then you got a puddle of water that's at 0 degrees Celsius. You got to heat that all the way up to 100. Then you got to take that water that's at 100 and the energy required to break all those intermolecular forces and turn it into steam. And finally, the steam can get a little hotter also. So those are the 5 steps. When we're dealing with temperature changes, like this one, 20 degrees of warming to get up to its melting point, let's use Q equals mc delta T. Because we have the mass, and it's always going to be 18 grams, we have the specific heat of water, but it's ice water, so don't use your 4.18. Use the ice, which is 2.03 joules per gram degree Celsius. I am going to skip the units, which I shouldn't, but God, there's so many of these things here, so forgive me. And it's going up 20 degrees. That's our delta T. Notice that? 20 to 0. Always use an absolute value because every step is endothermic. That cost us 731 joules. Now we've got to take that liquid water and bring it all the way up to 100 degrees. No. We've got water that's ready. We've got ice that's ready to melt. So let's melt it. Takes 334 joules per gram, and we've got 18 grams. It's going to take us 6,000 joules to melt that ice. Now it's at 0 to 100. So we'll do Q equals mc delta T. M is still 18 grams. C is now liquid water, so 4.18. And we're going the whole enchilada, 100 degrees. Costs us 7,000 joules. We now are ready to boil it. So we're at the boiling point. So let's use the enthalpy of vaporization, which is 2260 joules per gram, and we have those 18 grams, so that's a whopping 40,000 joules. That's like taking hot water on a pot and let it boil down to dryness. It takes a while, takes a lot of energy. Let's bring it up 10 more degrees. This time for our Q equals mc delta T, we'll use the 2.01 joules per gram degree Celsius. And we're just going 10 degrees hotter this time, and that takes 361.8 joules. We got to add all 5 up. Is there a question like this on the quiz? Sadly, there is. Add them all up, and you get 55,308 joules. Is that a lot of energy? Well, I know that nutritional calories I'm comfortable with. There's 140 in a can of Coke, for example. So this is only 14 nutritional calories because there's 4,184 joules in a nutritional calorie. So this is only the energy that you get from eating a couple of potato chips. That's energy in water. Here's another question on energy in water. It's probably the most challenging question on the quiz, and I'll give you a sample type question. See if this makes sense to you. We've got a chunk of ice. There it is right there. Let's put it in some warm room temperature water. So that's the water there. It's a smaller chunk of ice than it is room temperature water. 55 grams of water, 4.5 grams of ice. Let's assume it's all completely insulated. What temperature will this hit when it equilibrates? Well, it's not just a matter of a little bit of this and a little bit of that. If it was 4.5 grams of water at a different temperature, I'd just do a weighted average. But first, you got to melt that stuff, which takes 334 joules per gram. So let's see how many joules it takes to melt 4.5 grams, which should just be the 334.5 times 4.5. And then let's see how much cooler that makes that 55 grams of water. We can do that using the Q equals mc delta T. And at that point, you got some colder water and you got some warmer water that's gotten a little cooler, but not too much. Do a weighted average, and you should, when they mix, you should get what the average is. Notice that it's over 90% this big liquid water at this point. So like we said, it takes 334 joules per gram to melt ice. And we got 4.5 grams, so that's 1,507 joules of energy that must be used by that 23 degree water in order to make it a little cooler. So we'll use Q equals mc delta T for that, and that's for that 55 grams of water, which is going to lose 1,507 joules. That's our Q. Mass is our 55 grams. C is the specific heat of liquid water. Those are the units. Joules per gram degree Celsius. And that's 4.184. And the temperature change we're going to solve for. So I like to rearrange, which I just did. Q, as we said, is our 1,507 joules to melt the ice. And we have 55 grams of water that's going to get a little bit cooler, and 4.184 joules. Not that easy to change that temperature, so it will go 6.5 degrees colder or go down to 16.5 degrees Celsius. At this point, you got 55 grams of water at 16 and 4.5 grams of water at 0. So 90% plus at this temperature, maybe 10% at this temperature. So you could just, if it's a multiple choice question, look for something that's just, I don't know, just a little bit cooler than that. But to do a true weighted average, we've got to switch to Kelvin, because if we do anything times 0 degrees Celsius, we get 0, regardless of how much it is. That can't be right. So add 273 to get your Kelvin. That's a true measure of temperature, and then we'll go back. It's the way, whenever you do math on temperature, you got to use Kelvin. So first I figured out what the weighted averages are. What do they call these? The abundances, I believe. That's 7.6%, but we'll use an abundance, right? 0.076. And that should be 55. Get rid of that 4. 55 of the 59.5, so 92.4% of it is the liquid water that was a little bit warmer. And then you just do the weighted average. 7.6 at 273 and 9.924, 92.4%, if you will, at 289 is just going to be much closer to the 289. Look at that, 288, and subtract 273 from that to go back to Celsius, and it turns out that that cup of ice water that you had will equilibrate to come to 15.1 degrees Celsius. So the little ice cube made it comfortably cool to cool you off on a hot summer's day. And since this is a good time to put in our passphrase here, let's just simply have our passphrase be water. I hope you heard that. Let's talk about solubility. Now, when you throw salt or something in water, it will dissolve. How much? Some things more than others, right? Generally, as you heat them up, they become more soluble, right? You take a whole bunch of salt, put it in water, and as you heat it up, more of it will dissolve. It's not always true. There's these weird outliers that as you add them, they tend to precipitate. So it's not true that solubility increases with temperature, but any cook will tell you it usually does. Now, if you've just added a little bit and you could add some more, we call that an unsaturated solution. You're less than the maximum amount that you can maintain. A saturated solution is exactly the amount that can dissolve. It's surprisingly easy to do. If you throw in excess salt and water, the excess will settle to the bottom, and the solution above that excess will, by definition, be exactly saturated. No math required. You just let Mother Nature do it for you. Now, and if you're supersaturated, you actually have more solute than it can possibly handle. And it's surprising how often that happens. You take some hot water and you add sugar to it, and you can go way beyond what it's supposed to be able to handle. And it does that temporarily. And then at some point, it will pop back out. So it's just kind of a weird phenomenon. Let's answer two questions. You got a solution containing 40 grams of sodium chloride for every 100 grams of water at 100 degrees. Is that solution saturated, unsaturated, or supersaturated? Well, I just find the intersection on the graph, right? 100 degrees, that's right there. Sodium chloride, that's right there. And it looks like at 100 degrees you can handle exactly about 40 grams of salt for every 100 grams of water. Hey, that's exactly what they added. I believe they have a saturated solution. Try the next one, and I did pre-mark it for you. This time you got 50 grams of potassium chloride for every 100 grams of water at 25 degrees Celsius. So now we're at 25, so start right there and find your KCl graph, and it's the blue one, and you are right about at that point. It looks like it can handle about 35-ish grams for every 100 grams of water, but we've got way more than that. We put in too much. That's 50 grams. We would call that a supersaturated solution. Next topic. When you have solutions, and in the healthcare industry, I'm finally relating this to the real world. You're dealing with solutions all the time, right? Saline solutions and IV drips and you name it. So often anything you inject or work with is a solution. Two common ways that scientists measure them is mass percent, which is okay, but it doesn't include sort of big molecules compared to little molecules, and molarity, which scientists usually prefer because that's a true count of the molecules. So mass percent is just how many grams of, let's do salt water, for example, how many grams of salt you have, not divided by the grams of water. That's a common mistake. It's the grams of solution. It's the grams of salt plus the grams of water, the whole solution. Circle that, make a big point. Don't make that error that everybody else is. Turn it into a percent. Molarity also has solution on the bottom, but this time we do the moles of solute. So that's how many, truly how many molecules. Don't forget the mole is just a number. And let's do, since it's a solution that's typically liquid, we'll do liters of solution on the bottom. So you might have a 1 molar solution, etc. Typically anything more than 1 molar is oftentimes thought of as pretty concentrated. And what could I say about a mass percent that's concentrated? Geez, I don't know. 20%, 30%, maybe an 80% concentration. That would be very high, right? And let's do a couple problems. You've got some, let's see, 100.5 mil solution. So imagine both things together are 100.5 mils or 100.5 grams. So its density is 1 gram per mil. And it's a little bit of glucose in there, right? So we've got roughly 95 grams of water and 5 grams of glucose, so not much sugar and water. Can you picture that in your mind? Let's find that mass percent. I don't think it's going to be very high. Let's just plug in how many grams of solute. Solute means the stuff that got dissolved. I should have pointed that out, like sugar in this case. And that's 5.1 grams, and they did give you the whole solution in grams, so this is directly plug-in. There should be 100.5 there. There it is, 100.5 grams of solution. Turn that into a percent, and it's a 5% solution by mass. If we were asked to do the molarity of it, that's now we got to do the moles of solute. Now moles, you need a whopping 180.6 grams to have a mole, and we only have 5. So you could say we have 5 180ths of a mole. Do you get that? If it was 90 grams, we'd have half a mole. So there it is right there. That's how many moles we have. Very small number. And we divide it by the liters of solution. And that's a little cute there. You have 100.5 mLs. And maybe if you're in the healthcare world, you know that you need a whole 1,000 mils to have a liter. And so you only have 0.1005 liters. That's a tenth of a liter. Take that and make it 1,000 times smaller, 3 decimal places. So that's a 0.282 molar solution, and that's pretty dilute. Finally, it's not a bad idea to figure out how to make a solution. Find a procedure to make 100 mils of a 1 molar sodium hydroxide solution. Well, I could say it, but I don't think I could do it. I would take, let's see, I would take 1 molar. So I would take a certain amount of sodium hydroxide and add water until it's 100 mils. Makes sense? Don't say how much you're going to add because you don't really, you could, but it's assuming volumes are additive, which is a little bit risky to do. So I'm going to word it, take blank grams of sodium hydroxide and add water until it's 100.5 mil, which you could actually do. But how much do we need? Well, let's take 1 mole per liter, and we only have a tenth of a liter, and turn that into moles, right? So it's 40 grams per liter, right? That's 1 molar. That's 1 mole, 40 grams, 23 plus 16 plus 1. I did this in a quick way for every liter of solution. So that's a 1 molar solution, but we only need a tenth of a liter. So it's only 4 grams. If you're making a whole liter of it, use 40, but we only need a tenth of a liter, so use 4 grams. That's the key number you need. Take 4 grams of sodium hydroxide, dilute it to 100 mils using water. If you said add 96 mils of water, I'd give you full credit, but this is the most accurate way of saying it. A little bit about acids and bases. I believe we have 2 slides and we are done. We're going to talk about common substances, whether they're acids or basic, what is an acid or a base, and how can we measure it in a very precise manner. Well, as we've said before, an acid's something that contains H plus or in some way increases the H plus concentration of a solution. You typically do that using acids, things that begin with H, HCl, HBr, H2SO4, HClO4. Bases are the other part of water, not H plus, but OH minus. You add them and the pH will go up, right? It will increase the OH minus concentration. We call those hydroxides, sodium hydroxide, lithium hydroxide, etc. Look at these naturally existing substances, tell me what they are, and tell me if they're acids or bases. Oranges, acids, they have citric acid, for example. Lemons, same deal. Lemonade, same deal. The sugar added won't change it much. Tea, tannic acids, things like that. Milk of magnesia, which is magnesium hydroxide, so base. Baking soda, sodium bicarbonate. I don't see H plus, I don't see OH minus. It is a Bronsted base. Hydrogen carbonate or bicarbonate will add to water to generate hydroxide in solution. So it's a sort of tricky base. Batteries. Well, those ones look like alkaline batteries, and the term alkaline usually means basic. But you might have lead acid batteries, you might have any type of batteries. It could be either. Milk, you might guess that one. It turns out that you've got some naturally occurring acids in there, bringing it down to about 6.8. Does that surprise you? It did surprise me. Baking powder is sodium carbonate. Same reason as sodium bicarbonate, it is Bronsted base. Vinegar contains acetic acid, so it's acidic. And tomatoes, for the same reason, most of these fruits contain citric and ascorbic and different types of acids. Oils, for example. Now, it's worth mentioning those because they're not aqueous. Everything else was aqueous. We're going to say neither. They do not have a pH. They do not have H plus. They do not have OH minus. Neither do most rocks. Neither do, I don't know, a piece of plastic, things like that. Not everything in the world has a pH. So things that have a low pH are said to be sour or bitter. Fine. Aqueous are oftentimes slippery. Acids make the pH go down. I'll talk about that in a minute. Bases add OH minus and make the pH go up. Neutral, you might recall, is a pH of 7. And that is because when you have some water, the concentration, if you measured it, this is important, so this makes it all just tie together, at least for me. If you measure the actual H plus concentration in water, you'll find out that it's 10 to the minus 7th moles per liter. That's a mouthful. It's even worse to say 0.0000001 mole per liter. Somebody said, oh my God, can we just call it pH 1? That kind of thing, or pH 7 in this case, if it ended with a 7. So there it is. And when you multiply them through, it always is true for water that when you take the H plus concentration and you take the OH minus concentration, you'll get 10 to the minus 14th. But for now, let's just practice doing the math. If you take 10 to the minus 7th and multiply it by 10 to the minus 7th, we'll have to do that for this unit. You get 10 to the minus 14th. Knowing that, all we have to do is take 3 minus 7, 10 minus the 4th. Try the next one. That's right, 10 to the 10th. How about this one? That's right, 10 to the minus 14th. Notice that's a much smaller number than, for example, any of the other ones. And this one is huge. This number is 24 orders of magnitude larger than that one. Similarly, where are we? Let's try some more. If you have the same concentration of H plus and OH minus, it's 10 to the minus 7th. That means the pH is 7. OH minus is also 10 to the minus 7th. We can't have one without the other because it's sort of just like water splitting up. And so that will be a neutral solution. Its pH will be 7. N for neutral, the POH is 7. POH is literally the powers of hydroxide, which means the exponent there. This pH stands for powers of hydrogen, which is literally the exponent there, which is a 7. That's where it all came from. pH 8 means the H plus concentration is 10 to the minus 8th moles per liter. So there's a reason for it. All right, tell me about this. It's 10 to the minus 3. I guess the OH minus has to be 10 to the minus 11th. I guess that's pH of 3, which is an acid. I guess the POH, which only scientists talk about, is 11 because 3 plus 11 are adding up to 14. I hope you're seeing the formulas that can spit out here. Do the rest of these. That's right, 10 to the minus 9th. Yes, that is an acid, but it's a little bit weaker. It's closer to 7. And the POH, 9 plus 5 is 14. Here's another one. I think that's a basic solution, right? The H plus concentration is only 10 to the minus 13th. That's a pH of 13. That's above 7, so that would be a base. It would turn litmus paper blue, and it has a pOH of 1. So that's a little bit about how we do the math. That was a lot that took place on the quiz and the assignments. So if you go back to this stuff, you'll see this stuff a lot. So make sure you're comfortable with that. Last slide. Now, if I think Cortana just talked to me. Now, if you, whoa, this is the last slide. And this only covers, I think, 1 or 2 questions on the quiz. So there's a lot of learning here for very little questions. But if you want to get a great score, bear with me. Okay, thank you, honey. All right, so we've got pH plus pOH equals 14. We did that a bunch of times, right? 7 plus 7, 9 plus 5, etc. Similarly, the actual concentrations are the same thing, but it's an exponent. 10 to the minus 9 and 10 to the minus 5th will be true for that one. And so literally you could rearrange these and say that the H plus concentration, the true measure of the concentration, can be inferred given the pH. Just do 10 to the minus pH. Got to know how to do that with your calculator. Typically that means 10 caret button. I don't know if you're familiar with that. Minus 9 will give you a H plus concentration of 9? Yeah, an H plus concentration of 10 to the minus ninth. Yeah, there it is. And here, just do the same thing with pOH. Now, if you have the actual H plus concentration, you want to turn it into a pH, just take the negative log. So the negative log of 10 to the minus 7th is 7. The negative log of 10 to the minus ninth for like hydroxide concentration would be a pOH of 9. Take home message, just use these formulas to solve some problems. It's fine to use these on a test. Let's make sure you know what a log and an exponent is. And even if you don't, I'm going to show you. Logs. Well, do you know what 10 squared is? That's 10 times 10. That's 100. So we could say that 2 is the base 10 log of 100. It's that number there is what 2 is, right? So if we have 10 to the minus 2, that's less than 10 to the 1. It's less than 10 to the 0. So it's a small number. We make it a denominator. 1 over 10 squared, 1 over 100, 0.01. We say that minus 2 is the log of 0.01, just like we did up here. So logarithms are those exponents. Therefore, if the hydrogen ion concentration is actually 10 to the minus 2, which is, believe it or not, pretty high, the pH is 2. So the pH is the negative log of the hydrogen ion concentration, and 10 to the minus pH equals the H plus. Do the same thing with pOH. Fine. Now let's solve some problems. I'll give you the hydrogen ion concentration. You give me the pH. Very similar to the questions you'll have to answer on a quiz. That's an acid. The pH is 4. Well, I'm going to change that to 10 to the minus 1. That means the pH is 1. Now here, I don't think this shows up on the quiz, but just you'd have to take, let's see, we need pH. pH equals the negative log of whatever that number is. So type in negative, press the log button, and negative is not the same as subtract. It's oftentimes in parentheses on your calculator. Anyhow, punch in negative log of 0.84 and you'll get 0.075. Take the negative log of a 4 molar solution and look at that. You can get a pH less than 0. Let's go the other way. If the pH is 7, how much H plus is in solution? Only 10 to the minus 7th moles per liter. Such a low number. If the pH is 3, you've got more. Rather than 1/10 millionth, you've got 1/1000th of a moles per liter of H plus. 3.4 would be a little bit more still, so just take 10 to the minus 3.4 to get your H plus, and do 10 to the minus 12.62 here to get your H plus, which is exceedingly low. And if the pH were 7, 3.78, can we get the H plus? Well, I don't know. Let me just try H plus equals. Oh, good. Well, no, that does, yeah. H plus equals 10 to the minus 3.78. Punch that in, and you'll get that number. Well, pOH, really? Do you want that? Oh, I know. pH plus pOH equals 14, so I get 10.22. See that right there? OH minus. Well, if I got pOH, can I get OH minus? Yes, 10 to the minus 10.22. Very low number. Is it an acid or a base? Well, it's less than 7. It's an acid. Give me an example. That's considered a relatively weak acid, like maybe you'd get in orange juice. If it said pH 0.5, I'd say yikes, maybe like concentrated hydrochloric acid, something like that. That is a review of all the topics you need for this week's unit. As usual, email me if you have any question. Thank you for sticking with this long lecture.